Hello, everyone. Our project is the implementation of a genetic algorithm to the Frogger game. So the motivation for our project has been to pretty much learn how the process of genetic algorithms can be applied to a game through research and replication of the game and its code. So we chose the game Frogger, which is a very popular arcade game from the 80s that is still very popular today. And what we wanted to do was to create a population of players to play the game. And through that, we want to select the fittest through crossover and mutation so that a new population is created with the fittest individual. And just overall, we wanted to make an abstract subject of machine learning easily digestible by relating it to pop culture through a game that has very simple rules. So the term genetic algorithms um, has the goal of being able to obtain the fittest individual from a population. So how this works is you start off with a population where each individual represents a solution with genes encoded into the chromosomes. Then you have the fitness function, which is the determinant of how fit an individual is based on their fitness score. And third, you have parent selection slash mating pool, which is a selection of the fittest individual to pass genes to the next generation. So for this, two parents are chosen, and it can either be random, but it will most likely be based on the highest fitness scores. Um, Fourth, you have variation slash mutation, which is a randomly chosen crossover point chosen for mating. And for this, mutation may be necessary to preserve the diversity within a population. And finally, you have offspring slash best solution, which is the result from exchange of genes between parents. Usually the algorithm is complete when the offsprings no longer converge and there's no change from previous generation. This will, as a result, yield the solution to the problem or solve the game.
Regarding to the related works, before we come into our own method, in order to best define the problem of genetic algorithm creations and how to utilize it in games, we first need to define what the genetic algorithms are and how they are utilized in other literatures. According to one paper we find, a genetic algorithm tutorial by Darren Whitley, a genetic algorithm are a family of computational models inspired by evolution. This algorithm encoding the potential solution to the specific problem on a simple chromosome, like the data structure, and apply the recommendation operators to these structures so as they preserve critical information. So this type of algorithm models provide the idea of revolution of living organisms. They're creating generations upon generations of programming with a hope that next generation will become better than the previous one. However, there are a lot of similarity and differences between the genetic algorithms with living organisms. For example, unlike the living organisms, each generation can occur just like super quickly for the genetic algorithms, because each only need a few seconds to complete themselves. But similarly, as the biological chromosome in every living thing, the chromosome used to this program are randomly changed and then create the genetic drift and eventually enough genetic variation to cause each offshoot to try and solve some same problems in different ways. The thought is that eventually, through enough trial and error, the weakest link being terminated, and in the genetic sense, called Charles Darwin said, let the strongest live and let the weakest die.
In the paper, Combination of Genetic Algorithm and Neural Network for Independent Gameplay, Batista and others use a more advanced and robust version of our algorithm. They use neuroevolution. So instead of using regular chromosomes, they use randomized neural networks, which is commonly seen in more advanced game agents. This finding is very important because they found convergence within the fourth generation, and in contrast to us, when we find convergence within the 100 plus generation. There were similarities to our code, such as the roulette wheel, which is randomly picking a parent, and the mutation process. But the most stark difference was using a multi-layer neural network. So they found that the most optimal from breaking down the amount of generations was using 5 neurons only. And also found that they didn't need a XOR method, so they only use replication. In the paper, performance analysis of Flappy Bird playing agent using neural network and genetic algorithm, Mishra and others took it a step further, and they added they added a difficulty level, so even with a higher difficulty, the algorithm was robust enough to still converge within the fourth generation. And in the paper, learning to play like a human, uh, Miles and others were I noticed the genetic algorithm equated the shortest path as the most optimal path, while human players noticed that if they go around the danger zone in the game, they're able to find the most rewards. So they added a weight bias to the fitness function, which caused the genetic algorithm to mimic the strategy to mimic the strategy of a human.
The goal of the Frogger game is to reach the other side of the game window by avoiding cars, logs, and stepping on turtles to cross the river. A genetic algorithm is applied to teach the computer how to play this game. The important aspects of the algorithm include mutation, which is which direction each frog will take, the fitness, how far each frog gets, and the selection algorithm for the parents and the frogs themselves in the next generation. The selection algorithm selects the next generation of frogs randomly from the last generation with a range of the number of frogs to the total number of the fitness of the frogs. In this project, we have changed some parts of the code. The population of the frogs has been changed to observe its effects. Instead of having the program randomly select parents, it will, one, select the frog with the highest fitness, or it will randomly select a frog from the top 3 frogs, i.e. the frogs with the 3 highest fitnesses are recorded and one of them is randomly selected. In the original genetic algorithm, the population was decremented by 100 all the way down to 100 from 1000. The overall results showed no correlation pattern between the population change and the time and the number of generations it took for the program to finish. In the top left, the select parent function is from the original frogger.py method. A random frog is selected from the frog population to serve as the next parent in the next generation. In the bottom left, a modified version is shown where only the parent with the highest fitness is used as the parent for the next generation. On the right is the second modified function where the 3 frogs with the highest fitnesses are recorded and a random choice out of these 3 is made. This is to have it be more faithful to the genetic algorithm to introduce a little bit more variability and randomness, contrary to the select parent that only uses the best fitness. In the original Frogger game, the results were highly variable and very inconsistent. On the left, it only took 8 generations for the program to finish, while on the right, it took 195 generations for the program to find a path. This is likely due to the highly random nature of the selection algorithm, but it is very faithful to how the genetic algorithm functions. Unfortunately, the code that was changed to having 3 frogs act as the parents did not work out. It produced worse results than Frogger.py, and problems with this could include bugs in the rewritten function itself or problems with the original code. Promising results were shown, however, with Frogger bestparent.py, which uses only the best parent to produce the next generation of frogs. The results were very consistent, and overall it was quite fast. It is likely due to the more selective nature of the algorithm to use only the best parent as the next generation parent. However, it is less faithful to how the genetic algorithm works. In the scatter plot, in the box plot, we see that there was less variability when the parent selection was chosen based on only the highest fitness compared to random parent selection. And the top 3 frogs were excluded from this as the program did not finish. Less variability could be due to the bias for the fittest offspring, and a faster, more consistent convergence to the prime solution was able to be achieved through this.
Regarding to the discussion part, while the improved selection algorithm does provide a much faster route to the other side of the river, it's not entirely accurate to the concept of genetic algorithms. The reason for randomly selecting parents, it gives like the frog with a lower fitness value a chance. Additionally, it is not quite accurate to the natural selection as it is impossible for the strongest and most suitable specimens to become parents of the next generation. Another issue we find out during this whole process is that the improving parent selection can cause a early conversion error to occur. Unfortunately, throughout our trials, the attempts of randomly choosing among the frogs with the top 3 fitness cons has failed. In more than 500 generations, the frog have not made any significant advance towards the other side of the river. There could be a couple reasons of it. One reason is that it could be due to the highly random nature of selection or just the error in the code. Similarly, changing the population did not significantly impact the result from the Frogger pie, as we showed it previously already. Although our trials failed, we do come up with some potential possibilities for the future study. This including like researching why the Frogger top 3 pie is producing a worse result than the Frogger pie and the Frogger best parent pie. Additionally, it could also be interesting to look into the ways to further improve the efficiency of their algorithms, as well as finding ways to distinguish whether Frogger as parent pie is worth fitting with its parent selection algorithm.
Conclusion, as showcased, genetic algorithms are highly variable, with some generational leaps occurring early on, allowing for a swift conclusion of the game, or very dumb frogs who, after many, many generations, still cannot cross the river. Computers are specifically able to take more and more inputs and move at a much faster pace than humans. So eventually, I think that they can become better players than many humans over time, given enough resources and good enough programming. This is mostly only the case for simple games, because a delineated and clearly defined rule system allows a computer to know better whether or not they're doing poorly or well, meaning that generations can be more quickly adapted towards getting better points. However, games with more complex ideas like chess or League of Legends or Magic the Gathering would not only have to have much more generations, but they would also potentially not be able to compete with a human player until a huge amount of generations have been elapsed, maybe even not at all. However, that might change in the future, because as genetic algorithms are more and more studied and computers get stronger and stronger and are able to process a larger amount of data in a shorter period of time, there is a potential that the computers of the future would be able to beat any good player at League of Legends or Magic or chess based on purely a genetic algorithm. Thank you guys all for watching. I hope you guys have a great winter break. Here are some frogs.